Welcome to today's video. This is possibly the last video of the course, so I hope it's enjoyable. My voice is borderline making it, so let's see how that goes. In this video is the second part of the cosmology part that we talked about, the cosmology block. In this part, we're going to take what we did in the previous video, which is finding the form for the AMATH, Friedman, Robertson-Walker metric, which is the metric that corresponds to a universe that is homogeneous and isotropic. And then we're going to plug it into Einstein equations and figure out how does this universe evolve in time depending on what it contains. So what's inside the universe determines how this scale factor that has the time dependence of the metric will evolve in time. So we're going to deal with that. All right, so let's get to it. I designed it in the same way as the previous one, as an exercise. So let's do it as an exercise with several parts. Part A would be compute the Christoffel symbols, the Ricci tensor, and the Ricci scalar for the AMATH, Friedman, Robertson-Walker metric. Now, this is tedious because it's computing all the Christoffels. You can be a bit intelligent about it and compute less because there's a lot of symmetry in this metric. So I will not do all the arithmetic calculations. I have here the expression for the Christoffel symbols and then the Riemann tensor as a function of the Christoffel symbols. And the Ricci tensor would be contracting the Riemann tensor, and you will get the Ricci scalar contracting the Ricci tensor, right? So it's a lot of arithmetics, and I know it is a little bit cumbersome, but I think it's good to practice sometimes, so I recommend to get acquainted with it. I'm going to give you the results right now, and I'm going to tell you the clever way to do it, but make sure that if you have time, practice it. I think it's a good idea to at least a couple times compute all the, the Riemann tensor and the Ricci tensor and the scalar for one simple metric like this one. So let's get to it and do it. Here are the results, and of course the results again you need to compute them, but as you can tell there are many zero elements of the Christoffel symbols, and also you can tell that many are the same. Now the notation here is A is the scale factor A of t, of course, and A dot is the time derivative of the scale factor. Now, after having all the Christoffel symbols, you can compute the Ricci via the Riemann, but remember that it's a trace of the Riemann, so you don't really need to compute all the components of the Riemann tensor. This already restricts the fact that you're going to look at the trace is kind of the diagonal elements of the Riemann tensor in the first and third index that you need to check. Anyway, if you do it, for example, the TT component is this one, the II component is this one, and it turns out that the Ricci tensor, these are the non-zero components. Non-zero components. Maybe I'll write the whole thing. Components. The Ricci tensor happens to be diagonal in this spacetime. Very nice. So we have a diagonal Ricci tensor. You can tell already though that even if your spatial sections are flat, so k is equal to 0, and then you have flat spatial sections, which is what you hear when people say, oh, but our universe looks like it's flat. The spatial sections are flat. Notice that the curvature tensors are not 0. You do have curvature in the spacetime. You have curvature, even though the spatial sections are flat. All right, here's the Ricci scalar. The metric is diagonal, Ricci scalar is diagonal. Calculation is very simple, yielding this result. And notice that, again, even if k is 0, the Ricci scalar is non-zero. There is curvature, and that curvature changes in time. There is evolution of that curvature. Notice that this is the Ricci scalar for the full spacetime, not the Ricci scalar just for the spatial sections. All right, so we have all the Christoffels, we have all the Ricci tensor and the Ricci scalar. We are ready for Einstein equations. All right, so I compiled the coefficients of the Ricci tensor here and the Ricci scalar. This is the Freeman-Robertson-Walker metric here. And what we're going to do now is let's model cosmology as generated by a perfect fluid of density rho and pressure P. What does that mean? So let's assume that cosmology, well, the universe is evolving. We see expansion of the universe and we see things happening, things changing. The scale factor changes in time. Now, why does it change? Well, because the universe contains matter, and those matter fields are acting on space-time by generating, generating space-time curvature and space-time dynamics. So when those matter fields interact with space-time, they do it through Einstein equations. Now, it's a set of non-linear equations. So space-time tells matter how to move, and matter tells space-time how to curve, right? So let's say that the content of the universe is modeled by a perfect fluid. Well, is that okay to do? So basically we say the universe is full of stuff, but that stuff that is full of we can model it. Basically, there's not that much interaction between them, between the things that make the universe, the constituents of the universe. It looks like there's not that much. So what we can do is assume that it's a perfect fluid, and we sweep all the details, all the microscopic details of the different fluids in what will be the equation of state of the fluid. Of course, if this fluid is made of non-relativistic matter, the equation of state will have some form. If it's made of dust, non-interactive dust, the equation of state has a particular form. If it's made out of relativistic matter, like light, for example, or maybe neutrinos or something really hot in a way, then, well, then of course, you're going to have a different equation of state. So basically we say, okay, let's treat it as a perfect fluid. So let's assume there's not a lot of heat conduction going on and not a lot of viscosity, which honestly is a very good assumption for the matter that fills the universe at the cosmological level. And also, let's assume that this fluid, it's co-moving with the Hubble flow, what we call. What does that mean? Well, that fluid is going to be co-moving with the observers that see the universe homogeneous and isotropic. Why? Because that fluid has to be homogeneous and isotropic to live in a universe that respects those symmetries, homogeneity and isotropicity. So if I already assume that my universe is going to be isotropic and homogeneous, I need to assume that my fluid will be too. And that means certainly that is another point towards perfect fluid, because remember that perfect fluids were isotropic, and we proved that. So let's assume that this perfect fluid is co-moving with the frames that see the universe homogeneous and isotropic. That's nice, because that tells me that the for velocity of this fluid, it's going to be, well, 1, 0, 0, 0, with the indices up. Okay? Right. Now, something important to realize, I wrote here the temporal Einstein equation. So what is this temporal Einstein equation? Well, this temporal Einstein equation comes from substituting the RTT. So it's the component 0, 0 of the Einstein equation. You see, this is the 0, 0 component of the Einstein tensor, the 0, 0 component of the term proportional to the cosmological constant, and then I wrote here that should be the 0, 0 component of the stationary density. But it doesn't quite look like it, right? So what did I do? Let's write here what is T0, 0. So T0, 0 would be equal to, let's write like that, rho mu 0 with indices down, plus P mu 0 plus G0, 0, right? That's what it would be, just reading from here. But realize then that the metric here, the Friedman-Robertson-Walker metric that I wrote here, the G00 component, so the GTT component, maybe I should write T's rather, right? Apologies for my voice, it's at the verge of failing, but I can't delay posting this video anymore. So I'll try to do my best. It's the last video, so boys, please, boys, stay with me. Anyway, so T, as long as I have a shred of voice, I will keep doing physics for you. Sorry guys, it's a bit delirious, it's just the time it is and so on. Anyway, so this is the T00 component for the stationary density, but then we realize that because GTT is equal to -1, as you can tell in these coordinates, and the fluid is co-moving, I know that U mu is going to have, well, remember what U mu is. U mu is G mu nu U nu, which of course is only one component right in here, so it's going to be G mu 0 nu 0. So the 0th component of this is going to be G00 times U with index up. So if you want to write this because you feel happy about it as a row vector, well, why not? I mean, whatever at this point. So you have that, right? And then the U0 component is -1, the T component, right? So you get that this thing is -1, this is an overall 1, and then this is -1, this is an overall 1, and this is -1. So this is 1 plus -1, which is 0, and this cancels, and this becomes a 1. And that explains why A times pi G, the stationary density, component TT, component 0, 0, gives me just the rho. Okay, wonderful. Now, we also get the following equation for each spatial component of the reaches and the metric, right? They are diagonal. So we get here the spatial part, the diagonal part of the Einstein tensor, and the term proportional to the cosmological constant, and also the diagonal part of the stationary density, which is just the spatial diagonal part, of course, the spatial components, which is just, you know, this one, they don't have spatial components, it's a moving fluid. And this one is GII, the spatial components. So that's what we have here as well. Now what we do, of course, is substitute the expressions in terms of the scaling factors and the curvature parameter of the Ricci, of the Ricci tensor and the Ricci scalar, and also of the metric. And then we obtain, from the first one, we obtain this equation. And this is actually the first Friedman equation. Let me call it first Friedman equation. So those of you, I'm going to call this one 3. Or maybe the 3, I will put it here. All right. This equation is one of the results we're looking for. Those of you doing astrophysics may have seen it. Because this equation, by the way, you remember what this was from the previous video? This is the Hubble factor. Maybe you call it a Hubble constant, but how can you call it a constant if it's time dependent? Anyway, the Hubble function, the Hubble factor, whatever you want. You tell me what you call it in astrophysics. All right, so this is the first Friedman equation, and it's related the derivatives of the scaling factor with the scaling factor, and the density of the fluid, and the cosmological constant, and the curvature of the spatial sections of the universe. All right, now from the spatial ones, actually we get 3 equations, right? But the 3 of them give me exactly the same information when I substitute, which is this equation here. With a little bit of arithmetic manipulation, I get to this equation here. Now this is not the second Freeman equation. To get the second Freeman equation, I'm going to have to give a number to this guy, and the second Freeman equation I obtain by doing this. Multiply by 2 equation 4, and subtract equation 3, and I get this equation, and this equation is the second Freeman equation. Notice how the first Freeman equation tells you about the velocity of the expansion of the universe, right? This is how the scale factor changes in time, the first derivative. And the second Freeman equation tells you about the acceleration of the expansion of the universe. All right. So, yeah, we're getting closer to something that is related to our universe now. All right, okay. So these are the Friedman equations. So in principle, we've done what we were asked, which is find Friedman equations out of Einstein equations. So we have the equations that give you cosmology. But let's do something else too. Before we do it, notice that the relationship, the equation of state, how rho is a function of p, would actually determine how the universe would behave. The universe would behave differently if it's dominated by radiation, if it's dominated by slow matter, so non-relativistic matter, if it's dominated by a highly interactive matter, or if it's dominated by something else. Then I'm not going to talk too much about the different possibilities, because that's something that you will study in cosmology courses. We may have a discussion, and we will have a discussion probably in the discussion sessions, in the in-person sessions, and I want to keep some of the mystery for that. But again, these equations will tell you how the universe will expand, how it behaves in time. When you solve them, you solve for the scale factor and tell you what they are. And again, the kind of matter that makes up the universe, it will be encoded in this. Now you also have this cosmological constant term here, and that bothers me. Does it bother you? It's a bit funny, this cosmological constant term. Because it's like a positive contribution. So matter, look at this. Matter kind of tends, it tells me that the second derivative of A is going to be kind of negative, right? Because matter attracts, matter is kind of attracting, kind of like holding the expansion in a way, being very hand wavy, is negative sign is telling you. The contribution of the cosmological constant is positive. Cosmological constant makes the universe accelerate in this expansion. What sense can we make of the cosmological constant? So imagine that I want to make sense and say, no, this cosmological constant has to have from some sort of crazy matter, right? There's something that I don't know yet about physics that makes up this cosmological constant. So let's think of the following. If this cosmological constant came from a perfect fluid, what kind of fluid would it be? What kind of fluid would give me a contribution to Einstein equations equal to the cosmological constant? In other words, let's assume that Einstein equations don't have a cosmological constant and instead have some sort of vacuum energy, 0-point energy or something like that. It's still, in other words, the cosmological constant in Einstein equations on the left of Einstein equations. Let's put it on the right, on the matter side, and see what kind of matter equivalently, what would be the effective stress energy density that would generate a cosmological constant. Let's see it. All right, so Let's talk about dark energy a little bit. So these are Einstein equations with a cosmological constant. Of course, Einstein equations without a cosmological constant would be just this, pi g t mu nu, right? Whether you have a cosmological constant or not. Now, if you have a cosmological constant and no matter, you're in vacuum, then those are Einstein equations in vacuum. However, I can play the following. I can put the cosmological constant term on the right-hand side, like this, and then say that, well, if I do that, I get something like Einstein equations without a cosmological constant, but now not in vacuum. I have now a fluid, a stationary density, what I call the vacuum stationary density, and this T vacuum has to be lambda g mu nu divided by 8 pi g, all right? So basically, this is telling me that T vac mu nu has to be equal to minus 1 over 8 pi g lambda g mu nu. That's what it's telling me. So in a way, I can understand the cosmological constant. If I want, I put it on the right-hand side of the equation as some sort of vacuum stress energy. Now, let's see. So if I am bold like that and I say maybe the cosmological constant comes from some matter that I don't know yet, or maybe the vacuum of quantum fields, or what gets you? I mean, I don't know. But let's say that I try to understand it as matter, something that is generating it, which is more reasonable than just plugging in a constant in there just because I want a constant in my theory. It has to come from somewhere. All right, so what kind of, if I say for simplicity that this were a fluid, what kind of fluid would it be? What would be the characteristics of the fluid that would give me that kind of cosmological constant? Now, I discussed before that the cosmological constant that we observe in our universe seems to be positive, and in fact the expansion of the universe to be accelerating. What are the consequences of that? Anyway, let's see. So if I want the perfect fluid, if I want the T vacuum mu nu to come from a perfect fluid, let's call it like that, this thing is going to have to be a rho vacuum, some density, energy density of the vacuum, plus the pressure of the vacuum, then U mu, U nu, plus P, the pressure of the vacuum, G mu nu. All right? So the components, again, if this is a comoving fluid, if I write the components, what would be in the comoving coordinates, the components? T vacuum 0, 0 has to be equal. So the 0, 0 component, remember, is rho plus P minus P. Coming because this is a nu, minus P, because again, the 0, 0 component of the metric is minus 1 in Friedman, Robertson, Walker, right? So we get that this would be rho vacuum. Of course, I mean, we already saw it, that this is the 0, 0 component of stationary density is the energy density in that frame, in the frame that you're considering. All right. What about, maybe let's call it TT. What about the spatial components? Tij would be P vac and Gij, right? Okay, well, so if we identify, let's see what the components of, if we have this thing, let's compute rho vac and P vac for this case. So rho vac, so let's see, rho vac has to be equal to, again, T vac TT, the 0, 0 component, and that has to be equal to minus 1 over 8 pi G lambda, and then the 0, 0 component, so GTT. In the Freeman, Robertson, Walker universe, this thing is minus 1, that cancels the minus 1, so the density has to be a positive energy density, 8 pi G. There you go. That is the energy density of the fluid, of the vacuum, if you want, that generates a cosmological constant term. What about the pressure? Well, P vac, Gij, Gij would be equal to, and I write that, minus 1 over 8 pi G lambda Gij. Gij cancels, and I get that the pressure of this vacuum, if you want, would be minus lambda 8 pi G. Now, if lambda is positive, we have a problem. This fluid is funny, isn't it? So the fluid that generates a cosmological constant, this accelerated expansion of the universe, if it's positive, happens to be problematic no matter what. If the cosmological constant is positive, the energy density is positive, but the pressure is negative. If the cosmological constant is negative, you have a positive pressure, but then you have a negative energy density. And this is a funny fluid, very funny fluid. All right, you can tell what the equation of state is. The equation of state for this is rho equals minus P. Ah, that's a weird equation of state. This is a very funny equation of state. All right, okay, fair enough. Let's actually look at this from in the light of the energy conditions that we saw in relativity. Let's look at that. Quick note about the second Freeman equation. So I told you that the Freeman equation, like trying to understand, is like, yeah, matter. So the fluids that you have here kind of hold the expansion, so decelerate the expansion. You can think perhaps as the universe asymptotically stopping the expansion, or maybe even coming back, depending on the regime that you are, the kind of matter that you're having here, of course. And then I told you, but then you have the cosmological constant term, that what it seems to be doing is the opposite. This thing is accelerating the expansion, it's kind of repelling everything. Well, of course, that assumed that the cosmological constant is positive, which is the data that we have now compatible with observation. This cosmological constant, that we measure the cosmological constant, and we have, using data for supernovas. With supernovae are actually amazing for this, and we can discuss how these measurements are taken and how they're so cool. Mainly, there's a particular kind of supernova that happens when a particular amount of mass is reached, mass threshold is reached in a binary stellar system. And when that happens, the supernova goes off with the same intensity no matter when it happens. It's a very universal phenomenon. So then you know that you can actually measure distances based on the difference in luminosity when you get this kind of supernova. And that is great, because that means that you have a really, really good way of measuring distances from like distances that are really, really far away. And that allows you to measure this parameter pretty well, the acceleration parameter. So it seems that lambda is positive. The original lambda that Einstein introduced was negative, because Einstein got a universe that was expanding but decelerating the expansion, right? But he didn't like that, so he added a negative cosmological constant. It's easy to understand from Einstein's point of view. Let me just get back the first Friedman equation. If we look at this thing, it tells you that the velocity, the universe is expanding, and the content of matter of the universe is kind of contributing to that expansion, to that velocity of the expansion, to the magnitude of the expansion. Einstein didn't want that, and Einstein wanted the universe not to move, to be stationary. So yeah, add this thing and kill everything else. This thing will kill everything else. And if you have a flat spatial section universe, then to kill this, you need this to be negative. So Einstein actually introduced a negative cosmological constant. However, you see that when we measure it, the cosmological constant was dropped later on because Einstein realized it was a mistake to just shoehorn it in. We had to recover it because we measured an expansion of the universe that is accelerating. So it seems that the cosmological constant is positive. Because of experimental evidence, we see that the universe is expanding and is accelerating the expansion. We can talk a little bit about the consequences of that at the end of the video and in the discussion session, but I just wanted to let you know that, of course, the sign of the cosmological constant can go either way, positive or negative. It seems that it's positive for us, though. All right, let's go back to the video. All right, let's analyze whether whatever matter that generates the cosmological constant satisfies or not the energy conditions. And let's do it for the case of a positive cosmological constant, like the one we seem to be observing. And in the case of a negative cosmological constant, the one that Einstein decided it was okay to introduce to preserve a universe to be stationary. I wrote here the 4 energy conditions we saw, and the motto. I mean, I didn't write the null one because the motto is not that informative, but this motto is kind of a way to understand those conditions. All right, so let's see. Let's start with the weakest of all conditions, which is the null one. The null has to be satisfied in order for any of the others to be satisfied. Okay, so if we fail that one, we fail all of them. All right, let's see. It tells me that rho plus p has to be larger or equal than 0. Yeah, it's actually the sum of the two is equal to 0 always, whether it's positive or negative. So this is a yes and a yes. We always satisfy the null energy condition with the cosmological constant, with the matter that generates the cosmological constant that we're gonna call dark energy. We call that matter dark energy. And we don't know what it is, but let's call it dark energy, has to satisfy the null energy condition. Okay, cool. What about the strong energy condition? All right, let's see the two cases. So if lambda is larger than 0, let's see. Well, rho plus p larger or equal than 0 is satisfied because it's 0. What about this one? Rho plus 3p has to be larger or equal than 0. Ah, that's only true if p is positive. So in the case that you have negative cosmological constant, you do satisfy it, because the rho would be negative. So if the rho is negative, p will be positive, and 3 times p overcomes rho, okay? But in the case of a positive cosmological constant, this energy condition is violated. All right, we'll analyze it later. Weak energy condition. All right, rho needs to be larger or equal than 0, and the sum of the two larger or equal than 0. Okay, this is always satisfied. This is satisfied as long as rho, the cosmological constant, is positive. So in the case of the cosmological constant being positive, it is satisfied. It is not in the case that the cosmological constant is negative. Finally, we check the dominant energy condition. Rho has to be larger than equal the absolute value of p. That will be satisfied as long as rho is positive, not if rho is negative. So if the cosmological constant is positive, we satisfy. If it's negative, we don't. Which makes sense, right? Remember the chain of implications? The chain of implications was strong implies the null, and the weak implies the null, and the dominant implies the weak. Right. So if you are violating the weak one, you're not going to be satisfying the dominant, obviously. In order to satisfy the dominant, you need to check this one as well. Okay? All right. So let's analyze the consequences. So for the universe that we live in, we are violating one of them, the strong one, that tells you that gravity is attractive. Well, it makes sense. This thing, the content of energy density in the universe, is kind of pushing the energy away and making it accelerate. That is weird. The one that Einstein introduced violates the weak and the dominant. So yeah, it's weird. It's Einstein. I don't know why Einstein accepted this. We know they're violated, by the way. We know that they are actually violated by quantum matter. Quantum matter that we know, not dark energy or crazy exotic matter or anything like that. No. I'm talking about quantum field theory. Quantum fields violate them. But Einstein just shoved it in and accepted the consequences that may come with them. And the consequences are not nice. So there was no good reason to demand the universe to be stationary, paying the price of introducing this thing. Importantly though, the strong energy condition is violated for a positive cosmological constant. Now, what is the matter that produces that cosmological constant? That is unknown. It probably comes from the interaction of quantum field theories with gravity for real, as in whatever gravity really truly is. And as of today, we don't know what it is. We can talk about what kind of equation of states would be like that, like rho equals minus p. Rho equals minus p as an equation of state is weird. And we call things that satisfy that kind of stuff exotic matter, and we don't know what it is. That's why we call it dark energy. Not to confuse with dark matter. Dark matter is a different thing, okay? That we can talk about a little bit in the review sessions, in the live sessions. It's not part of the course per se, but at the very least, understanding what a cosmological constant does to Einstein equations is. All right. I think that with this, we have finished this video, and my voice made it to the end of the video. Yay! This is the last one. I hope that this course was enjoyable. I hope that the videos were easy to watch within reason. I know that teaching online is not the most optimal way of doing it, but I think it's nice to have a course put out, an introductory course to general relativity out there on YouTube for everybody to see. So anyway, thank you for all the feedback that you're giving me. Thank you for all your patience and the help. And I'll see you probably in the last, or I don't know if it will be the last, but in the next review session. And I hope that we can discuss about what you thought about all that we see. Because that's a lot. General relativity is amazing. It's like listening to Beethoven. Anyway, I'm gonna go because my voice is gonna explode. Thank you very much for staying with me throughout this course. And I don't know, until the next time I see you. And until then, please do take care. Bye-bye.